Hello, it's Keith here, and this is lesson 107 of the platform-specific series of my Z80 assembly programming tutorials. We're looking at the Game Boy today, which is not really a Z80, it's close, but it doesn't have all the functionality. But I've ported my MaxTile program to it anyway. MaxTile is a software tile map. Of course, the Game Boy has a hardware tile map, but we're sort of translating the functionality. The functionality MaxTile provides is Xflip, Yflip, fill tiles, which you can see there, and double height tiles, which you can see there. Now the Xflip and the Yflip are being done by the hardware tile map of the Game Boy Color, and that's why this doesn't work on the Game Boy. Some of the functionality would work, but the Xflip and Yflip, without the hardware capabilities of the Game Boy Color, we would have to pre-convert the tiles and store alternate copies of them. And as the basic Game Boy only supports 256 tiles, that would leave us with only 64 tile patterns in total, and that's not even thinking about the double height ones. So that wouldn't work so well. So we're only using the Game Boy Color today. Anyway, that's the example. Now, one thing I should point out is the large objects moving around the screen are simulated sprites, which are just drawn with a tile map. There's no hardware sprites being used in today's example. Anyway, let's go over to the code and let's take a peek. Okay, so the file we're looking at today is this GBC MaxTile mid. That's the example you just saw running. And the tile drawing routine that actually sets up the tile map is GBV1 MaxTile normal. Now, the way MaxTile works is it uses 3 caches to remember the updates that need to be drawn to the screen next time. So we're defining some memory for those. We're also defining the base tile pattern offsets for the different kinds of patterns. There are the basic patterns, which we're starting from offset 6, the fill patterns, which start at offset 0, and the double height ones, which start at that address there, 32 plus 6. That's the first tile number for the double height tiles. That's because that's basically how many tiles we need for the background. 32 background tiles plus 6 for the fills. So that's why we're using that offset there. Now, basically what we're doing here is we're going to define the patterns within the pattern data and then draw them to the screen. So the pattern data, we've got these routines that are initializing it. So we've got this fill data, which is the solid fill bytes there. We've got these general background data, and then we've got the character data here. The background data we're also defining as double height. So we've got these different routines that do these jobs. If we look at the end of our code somewhere down here, here it is. Here is the fill data, so two bytes for each line for the 2-bit planes, and then the sprite data for the various kinds of sprites in the background here. And these are 2-bit planes again, 8x8 pixel. Now, when it comes to defining the patterns, we're using these define pattern routines. This is the basic one. So this is basically just transferring all of the data into VRAM. And then we've got the double height one. What this is doing is it's basically writing each source byte twice by doubling the height of the tile. So you get these kind of stretched patterns there. And then the fill one, which is just reading in a single pair of bytes here and repeating 8 times for each of the tiles. Now, when we run these routines, we're passing various data. So we're specifying a destination address. Now, 8000 in memory is the actual VRAM for the pattern data. We're defining C as the number of tiles and HL as the source pattern data. Now, I'm doing a bit of a trick with regards to the DE destination though, because on the original Game Boy there were just 256 tiles, but the Game Boy Color extended this to 512. However, the extra pattern data is in a second bank of memory. Now, I'm using the memory addresses 8000 for the first bank and 9000 onwards for the second bank. However, that's not actually true, and what I've got is these routines here, which are checking the destination address, and they're basically switching the second bank on here and then resetting back to memory address 8000. And this one off is doing the same. We're using IXH, which is a fake register. This would exist on the Z80, but on the Game Boy, I'm using some RAM to simulate these registers, and so that is being used to remember if the secondary bank is turned on. And we're using the Game Boy Color hardware register FF4F, which turns on the extended functionality of the Game Boy Color, paging in the second bank here for the extra patterns. So you can see here at the start of the patterns, we're turning the bank on here if we need to, based on the DE memory address. And at the end, we're correcting the DE memory address and turning the bank off as required here. So these are doing the job of defining the solid fills, which just use 2 bytes per pattern, the double height, which uses each source line twice for the destination patterns, and the basic patterns here. The Xflip and the Yflip, those are done in hardware. When we turn on those extended Game Boy Color functions, 2 of the bits define the Xflip and the Yflip functionality, so that's how we're doing those. Now, when it comes to setting the tile patterns as being visible on the screen, we need to use the Tilemap, which is also in VRAM, which is in regular memory. So 9800 is the address of the top left visible tile of the Tilemap. So when we want to set the tiles, we would use that. We are defining our coordinates in logical units, which on all of my tutorials these days I use pairs of pixels as logical units. So in this system we're going to be converting those to tiles. In effect, the screen is 160 by 144 pixels, which is 80 by 72 logical units. Now, when we want to draw the simulated sprites like that character moving around the screen, we will need to calculate the VRAM destination in the Tilemap based on the logical unit coordinates. So we're converting the logical units to tiles here, and then we need to convert that to a VRAM destination. So 9800 is the Tilemap base. Each of the tiles on the screen uses 1 address within that memory. There's actually 2 bytes, but the second byte is at the same address within the extra Game Boy Color paged in memory. So we effectively just add the X position in tiles from 0 to 31. We multiply the Y position by 32 here, and we just add those to the VRAM base, and that is correctly calculating our VRAM destination. The draw tile routine is actually responsible for defining a tile on the screen. Now, the way MaxTile works is that the BC tilemap is the MaxTile source tilemap, and this defines what needs to be drawn to the screen. Each entry in there is 2 bytes. Now, the least significant bit of the first byte is basically the update flag, and if this is 0, this draw tile routine is never executed. If it's 1, then this will be executed, but when this starts, that update flag is shifted out of the byte in the accumulator, and that's because we want to clear it back to 0 for running this routine. So when we're testing bit 0 here, we're actually testing what was originally bit 1, and that's the program bit that defines if we're using a special kind of tile. The MaxTile draw tile routine works as basically a binary tree kind of structure, where the most common, simplest routine is executed first, and then we go to sort of successive layers of complexity for the more advanced routines, and that's so that the most common routine is the fastest executed with the fewest comparisons and branches. So that's what's happening here. Now we're taking our top 4 bits of the least significant byte and the remaining 8 bits of the second byte, and these are our tile number. Now this is effectively pre-multiplied by 16 because it's designed for 4-color systems. However, because of the way the Game Boy Color and the Game Boy work, we actually need to effectively divide this by 16 and move the tile number into the bit 0 of the low byte, and maybe we want to use the first bit of the second byte if we're using the Game Boy Color's extra tiles, but basically the top 3 bits here wouldn't ever really be used in this example. What we're then doing is we're adding the DE from our fake shadow registers. The Game Boy Color doesn't actually have shadow registers, so we're storing those in 2 memory addresses here. And this is the base for the tile number for the character we're drawing. So the Yorita character can use different graphics to the Chibico character, and the background can use different ones again. So that's what we're doing here. Now, we've got 2 bytes here, and we are actually going to write 2 bytes to VRAM, but there's a problem because this bit here, which is the bit 8 of our tile number here, actually needs to be in a different position because the bottom 3 bits of the second byte are actually the color number. So we need to move that bit to here, which is the bank number. So we're shifting that bit here, effectively moving that into the correct position, and then storing that in D. So DE is now our tile number as we want to write it into VRAM. So we're then just waiting for the VRAM to become available. We're then writing the first byte into the classic Game Boy memory. We're then turning on the Game Boy Color's extended bank here and writing the second byte into that, and then turning that bank off again. So that's basically defined our regular tile there. So that was pretty straightforward. So that's our basic tile. Our advanced tile routine is executed if that program bit was set. And now what we're going to do is we're going to check what kind of advanced routine we're running. There's 2 bits defining X and Y flip, or X and Y flip, which is of course a thing. If both of those are 0 though, then this is what's known as a custom program, and so we're going to branch out to that code and look at that later. If we get to this point in our code though, we're doing some kind of flip. We don't know which yet, but we'll figure that in a moment. Here we're clearing the update flag of the tile map, and then we're getting the bits of our tile number again and shifting them into the correct position here, adding our tile map base, our tile pattern base there, and again shifting that RAM bank bit into the correct position here. We're then reading back in our tile number here because we now need to see whether we're doing an Xflip or a Yflip or both. So we're testing the Yflip here, and if that's not set, we're just doing an Xflip. Now, because of the way the Gameboy Color has that nice hardware functionality, all we need to do on this system is we simply write the first byte as before, page in the second bank, and then we're just setting bit 5 of D here, and that is affecting the Xflip here. So we just write that, turn off the extended bank there, and we're done. So that's the Xflip. The Yflip, very much the same. We're checking if we're doing an X and Yflip. If we're not, we simply set to bit 6 here, write the extra byte there. Very straightforward. And if we're doing the X for Yflip, we would set both bits 5 and 6 here. And then that's it. So X and Yflip basically all handled by the hardware, which is why this is so easy on the Game Boy Color, and it would be so hard on the classic Game Boy. Sadly, the classic Game Boy hardware was a little bit limited, but for the time you can't really complain. Now the custom tiles, basically we've got 3 kinds of custom tile. We've got solid filled tiles. These were designed basically to save speed mostly on the CPC systems like that. We also have double height, which was designed to save source pattern data by stretching 8 bytes into what would be filled with 16 bytes on the screen. We were effectively halving the source data, which is often worth doing on systems with 64K of memory. And then the final one was transparency, which we can't really do, but the Eureka character here around the feet, there's no tiles filled in, and that's because those are transparent unused tiles, and that's also handled by that transparency routine. Generally speaking, though, for this system, very straightforward. Though basically all we're doing here is we are taking the DE pair here, and we're just adding the offset to the double height converted pattern data. The data's been converted in advance, so we're just switching to that alternate data here, and then we're just writing that as before into the tile map here. The fill is exactly the same again, just using the fill data, writing that in again. And then the empty one, unfortunately we can't do any kind of clever transparency, being as we're not using hardware sprites here. So all we're doing here is we're checking for the empty byte here, which is a byte of 255 here is the empty completely unused one. In that case we're simply returning. Otherwise, being as we can't do any kind of transparency just using the tile map, with hardware sprites we could, but without them we can't. So we're just drawing the tile to the screen as is there. And so there we go. So this does allow us to use all of the functionality of MaxTile on the Game Boy Color. Now, to what extent this is useful, I'm not really sure. The difficulty would be, for me, the Game Boy not using a true Z80. There's a lot of work involved in porting my code to it because I have to make a lot of replacements of native code, Z80 code with macros that do the equivalent on the Game Boy. It's a lot of work, and the other problem is the Game Boy screen is so small that any game designed for a 256 by 192 screen is not going to work on this system without radical modification. This was really just a proof of concept. The MaxTile series is all about defining a set of things we want to do and then making all of the systems do them with it in whatever way is most appropriate for that system, and that is the result of this one. One thing it could be useful for, though, is I'm now working on another project which is an 8-bit virtual machine. Again, that'll be fun to port to the Game Boy Color's processor, but that uses a graphics routine to draw text and the graphics to the screen as a result of that virtual machine's processing. The idea being you can write a game once in this virtual machine's instruction set, and then it will run on any system, whatever the processor and whatever the graphics capabilities. So, MaxTile could be very useful for that because MaxTile is one of the graphics routines I'm using with that virtual machine. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.